This chapter discusses an algorithm for increasing the resolution of a single image using the SparseLand model. We start our discussion of the single image super resolution problem by defining the task and the rules of the game in terms of the solution we propose. The image YH is a high resolution image we are interested in. This image undergoes a blur H and decimation, that means sampling S, followed by a contamination by noise, and this leads to the image we do get, ZL. This is the algebraic connection between the measured image ZL and the one we would like to recover, YH. By the way, in our notations, H stands for high and L for low, referring to resolutions. Our goal is to design an algorithm that will use ZL to get as close as possible to YH. We are about to propose a recovery algorithm, but before doing so, let's define the rules of the game. When we reconstruct YH, we have access to the image ZL, obviously. In addition, we will assume that the degradation operators S and H are known, along with the knowledge of the sigma, the level of the noise. If these are the only known ingredients, then the solution would be very poor. Another critical piece of information we have is that YH is a natural image, and thus a good choice of a prior could direct the recovery process smartly. Naturally, we will use SparseLand. Okay then, now we are ready to propose a solution. First, and just for the convenience of later expressions and descriptions, let's start by a plain interpolation of the image ZL to become YL, a low-resolution image of the same size as YH. We will design our recovery algorithm so as to start from YL, and this way there will be no ambiguity in the correspondence between pixels in the input and the output images. We denote this interpolation by the linear operator Q, standing for bicubic interpolation. How can we bring SparseLand to this task? If you were to design a single image super resolution algorithm based on all that we have seen so far, what would you have done? Probably the first method that comes to your mind is P0 epsilon all over again. Look at this formulation of the problem. It makes a lot of sense. We search for the sparsest possible alpha to represent the desired image, such that after a blur and decimation it is close to the measurements. We assume here a global model on the entire destination image, and D could be the Har or any other transform that makes sense to you. This is a simple and direct extension of the global deblurring algorithm we already presented. And you know what? This could work. I'm not expecting state-of-the-art results from this method, but it would have given nice results. Here is another option, very much in the spirit of the things we have done when migrating from global to local modeling. This approach imposes SparseLand on the resulting image patches while requiring, as before, a small error between ZL and its simulated version. I'm not sure how this should be solved, but I'm sure that this is doable, and you know what? It should be done. Strangely enough, it was not proposed in the literature so far. The method we are about to present is different, very different from the above two. In this chapter, we describe a third option, still harnessing SparseLand, and yet doing it in a way that is different from the above two more expected techniques. The method we promote is still patch-based, and as such, it will include in it learned dictionaries. The core idea for this method was presented in a paper by Young and his co-authors in 2008, and we will present a slightly different and improved interpretation of it as reported by Zaide in 2010. Why are we going with this specific option? Because it demonstrates the richness with which SparseLand can be practiced, and also because it leads to very good results. And now to the core idea of this method in a nutshell. We have the image YL, and our dream is to get from it to the image YH. I remind you, those two are of the same size. We will operate on patches in YL, processing them one by one, and then aggregating them to create the image YH. And now to the true engine of this method. How can we enhance the patches? We start from low resolution patches, and we will apply sparse coding to each of them with the help of the low resolution dictionary DL. Given the representations found, we will simply multiply them by the second dictionary DH, and this will create the output patches. Clearly, This approach calls for the design of DL and DH jointly. Moreover, all the inversion effect of the blur and the decimation is encapsulated in these coupled dictionaries.